All right, let's get started. Before we dive into today's topic, any questions on the homework?
Yeah.
Okay. So today I wanted to discuss in a little more detail how locks really are implemented. If we look at pthreads, for example, we look at semaphores, which are actually part of the pthreads library too, as far as I understand it, but they're just not included when you include pthreads. They all use what's called futex in Linux. So you can implement this in different ways, I suppose, but Linux is sort of what we want to look at here because all the sources are available, which is great. So the idea here for a user space lock implementation we have this difficulty, right? So far we've talked about, how can we do a lock? Well, we use these atomic operations, compare and exchange, or test and set. It's easy, right? But then the problem is you're always spinning, right? That's what these operations do. So initial implementation, compare and exchange, and spin, right? So it might look like, okay, while not compare and exchange some value 0, 1. Okay, so here the operation, this is of course a little abstract, but this compare and exchange, it takes, mutex is just a place in memory, right? It's just a variable in memory, and it says see if it's 0, right? If it's 0, then replace it with 1. If it's not 0, then it won't do anything. And then it returns the value that it was before. So that's usually the case with these atomic operations. It returns whatever it saw, not whatever happened. Because we know what's going to happen. But we don't necessarily know what was there before it happened. So this is a spin lock. Right? And the difficulty with the spin lock is that it uses a lot of CPU. It's just going to sit there forever until some other CPU, assuming you have multiple cores, until some other core comes and sets this value to 0, or until the operating system decides, okay, you've had enough CPU for a while, it's time to run a different process or a different thread, and then that process or thread might set the value to 0. Right? So there's two possibilities. You have the multiple cores running, or you have this interrupt. Those are always the two sources of concurrency. You have either actual concurrency, or you have some outside signal just stopping you and letting someone else run on the same CPU. Either way, we have this problem that we're going to run until the interrupt happens, or until someone else changes the value. We're going to just keep checking this variable.
We're checking the mutex.
Well, okay, so I call it mutex, but let's call it mutex integer, right? It's just an integer. So
this signifies whether someone's looking at something or not.
Yeah. So okay, so let's call this. This is our lock implementation. Right? Mutex. I'll just go like this. And this is actually an int star mutex. Right. So now this compare and exchange takes this address for this int, and it decides, well, it's only going to return when the variable is set to 0. Then it sets it to 1 and returns. Right. And what's unlock gonna do? Any thoughts? Anyone? Ooh. Okay, so we say while. This is a good start. It's probably not a good start, actually. Unlock doesn't block, so we don't really need a. What's that?
I mean, you already have the lock, so you set it to 1.
If we set it to 1, that means it's taken. So we want to set it to 0.
Oh, yeah.
Yeah. So I'll say mutex equals to 0, right? Of course, I do the star mutex there because that was a pointer, so I dereference the pointer. Hopefully everyone follows that. Okay, so I didn't need to wait or do anything here. I hold the lock. No one else is going to get to mess with this. And besides, assignments happen to be atomic. So it's not like, oh, I assign the first byte of this 4-byte integer, and then someone else comes in and integrates the lowest byte. Increments the lowest byte. That doesn't happen. You assign the whole thing at a time. So I looked around a little bit, and I was not able to find any architecture where assignments of integers are not atomic. So that's always the case. By the way, you can't trust that if you do an assignment of a struct. Right? So you do in C++ or in C, you can say like, oh, struct A equals just B, or struct large type A equals B, and B was another large type. Here, this is not atomic. You want to know why? Exactly, yeah, we looked at this before, right? How does this assignment work? It's a loop sometimes, or sometimes it's just an unrolled loop. It's just a whole bunch of move operations. So every one of those moves is actually atomic. At least on Intel, you can either move in or you can move out of memory, but you can't move from memory to memory. So in this case, we'll have, we might be able to move the first few, and then someone else comes in and changes the last few at the same time. So that's no good. In C++, the most recent standard, there's also, you can do atomic assignments. But you have to tell it that you want an atomic assignment. So look at that if you're interested. Okay, so this is our entire spin lock. And I think, well, you know how things go with these, when we're talking concurrent programs, probably there's a bug in here. Even though it's so simple, but I can't see it now. So the basic idea is this. So the main difficulty with this implementation here is that, we're spending a lot of time executing this semicolon here, right? Over and over and over. It's never free, right? And every time it's not free, we have to go back and check. And every one of these operations is actually quite expensive. I'm not sure that it matters that much in this case, whether it's free or... we would just run more of them, probably. Okay, so the solution to this, let's see. So spin locks always spin. Actually, it's good sometimes. Anyone remember? When's a spin lock a good thing? Seems very wasteful, right? Okay, yeah. If it's very urgent, a spin lock might be the right solution. But I'm also saying it's very efficient sometimes.
When we're expecting a short break.
Yeah. If these locks, if someone's grabbing a lock, incrementing a variable, releasing the lock, if we know that that's how people use this lock, then a spin lock is great. Because it's going to take only a few instructions before they are done. Whereas if we're doing this other alternatives, it's going to be thousands of instructions probably before we even get back to running. Okay, so actually very efficient when critical sections are short. Okay, for longer critical sections, solution is called, in Linux, called Futex. So this stands for Fast User Space Utexes, I think. So fast user space. Okay. So it's a very simple API in Linux. It's a single system call, and it gives us all of the stuff we need in order to also schedule or control scheduling of our process. So in this case here, what we would like, something that looks like, let's see. here, if the lock was taken, then we probably want to wait, if there was such a thing, Qtex wait, right? And maybe we give it a variable, and then on the unlock, we would probably want to wake up whoever's waiting, right? If we have these two functions, we should be able to have a much more efficient. Oh, let's skip that. We'll have a much more efficient solution, and this also gives us the chance of doing other optimizations. Like we could try maybe spinning for a little while. So this is all running in user space. This is our code. We can write this. You don't need to be a kernel developer to use a compare and exchange. That's available to anyone. So we could say, okay, let's spin for 100 cycles, and then we go and wait. Or we might want to implement completely different synchronization operations. And these Qtexes, they give us this very basic control. You can say, wait for an address. Right? You just give it an address. It's a 4-byte line address. And then you'll just hang forever until someone comes and says, signal with the same address. And then you'll wake up. Actually, it's not called signal, it's called wake up. Just because we need to have lots of different kinds of names for these things.
It has to be a different address in the mutex.
No, it's the same one. So internally, we maybe don't care that much how it's implemented in the kernel, but it actually keeps a little hash table saying, okay, for this number, for this address, is there anyone waiting? So whenever you call wait, you get inserted into the hash table for some address. You can have multiple entries for every address. And then for the wake up, it goes to the same hash table. It just finds if there's anyone waiting for that exact address and wake them all up. And what it means to wake someone up, well, when you call wait here, you're stuck in a wait queue. Right? You're just sitting there. You're never going to run. You're sitting in a queue where you're never going to run, just like you're waiting for an I/O device. You're never going to run until something comes in on an I/O device. But then once you get a wake up, now the kernel goes through this list, puts everyone in the wait queue onto what's called a ready queue, which means eventually you're going to get to run. Right? When the CPU becomes available, when it's your turn, you'll get to run. So that's at an abstract level just what Qtexes do. But I think we need to we should look in a little more detail at what's really available here. So there's actually, I'm referring here to a paper. I'll put that in here as well. It's an interesting paper by what's his name? Ulrich Drepper at Red Hat. So there's some people at Red Hat that actually they do more than just package management. They have a bunch of kernel people as well that contribute directly to Linux. It's an excellent paper. Take a look at it if you want. It's relatively introductory. So anyway, let's look at sort of what's available to us in order to implement our own. So I wanted by the end of today, hopefully we'll have an understanding of how an actual pthreads lock works. I think we disassembled some code before. Let's not worry about that. Right? But we want to see this pthreads mutex lock function and mutex unlock. What do they really do? They actually all use this Qtex stuff. So there are a few functions that we need to have before that. Here's something that you may have seen. Atomic increment of a variable. So that's an integer, usually. Anyone seen this? Atomic increments? I mean, we've been dealing with this I++ problem over and over here. We're saying, oh, increments are not atomic, so it doesn't work. Here's a magic atomic increment. So why don't we just always use atomic increments? They're really slow. Yeah. Why are they really slow? Yeah, but we do the same thing. Our regular increment reads and then sets. Yeah, so there's no such thing as like the locks that we deal with now in the hardware. But there's something similar. So there's a couple of options you have. If you're on a single core machine, you can turn off your interrupts. Right? You just disable interrupts, the timer isn't going to work, I/O isn't going to work, nothing's going to work. But you can at least increment in peace, and then you enable the interrupts again. So turning off the interrupts, that's a bit of a big deal. Because there might be something in progress at the moment, so you have to wait for that to finish up. And turning them back on might also be a little bit of a problem, so that'll take a little while. If you're on an SMP machine with multi-core or multiple chips, then they actually have to tell each other, don't touch this physical memory address now. We're not talking about virtual memory addresses, it's a physical memory address after the page table and all that. And say, okay, this cache line actually, usually. So these 64 bytes, I'm the only one that gets to touch it. And then they go and read it and increment it. So that's sort of like a lock. But the problem here is now you have to tell these other CPUs that they can't use it, and that becomes a large coordination problem. And you also have these pipelines that start messing with you. Maybe you recall from probably you talked about pipelines in 261, right? Yeah. So this confuses the hell out of your pipelines. They have to clear out before you can get an atomic operation going, and so on.
Why wouldn't you be able to just, in memory, mark it? So like anytime someone tries to edit memory, they first check some bit, like, oh, can I edit this now?
Good question. Yeah. So why don't we just mark it in memory like that?
Most of the time, we
So assignments to memory are atomic. So you'd think we could just assign some other bit here.
someone could change the thing also, the bit.
Yeah, so we can make we can have, for every piece of memory, we can have a bit, a separate bit that says, is this locked or not? And then there doesn't have to be any coordination between the CPUs. But of course, now you'd have to do an atomic assignment to that one. How do you know that that one's okay? You first have to check it.
Yeah.
All right? So you have to do a compare and exchange, and now we're kind of back in the same. Okay, so atomic increment, there's actually, and I thought this was interesting. So it's not something that's usually available in C. And the reason is not all hardware architectures support it. So what happens is this is available in the kernel for sure, and it's implemented many times by people who really know about the hardware they're targeting. So if you're doing a pthreads implementation, you actually worry about, oh, this is assembly, right? No, sorry, this is x86. x86 assembly, okay, I'll do it this way. Because you're anyway doing your compare and exchange and stuff that's only available in certain architectures. But it's not something that you typically do if you're writing a hello world. Because the hello world won't work on all these different machines. At least that's my understanding. So Atomic Inc. I was not able to find a cross-platform implementation of Atomic Inc. But actually not in user space. But I did find them in the kernel. So let's take a look at what they're like. How do we? Let's see. I don't know if you've ever used this excellent resource called LXR before, but you certainly will when you get to 385. At least if you take it with me. So. LXR is a Linux cross-reference. And here we have a few implementations of Atomic Inc. Let's look at x86. So this is Linux kernel code. It's part of the architecture-specific parts of the kernel sources. Actually, I'll just give you a quick look here. So this is the entire Linux kernel development tree. And now we're looking inside of, actually, it's kind of nice. So we'll go architecture. So here are all the different CPUs that are supported by, or architecture types that are supported by Linux. We go x86, and we go probably kernel. With any luck, we'll see an atomic in here somewhere. Is it in CPU? Ah, drat. Where is it? It should have been there. Anyway, I had the link, so where is it? Oh, it's an include. It wasn't in the source, it was in the include side. Anyway, so here's what it looks like in x86. Right, so we got there's an increment opcode. Now that one isn't typically atomic. So in x86, there's an opcode that does all of the work for us. It fetches the value, increments, and writes it. But it's still not atomic. So it becomes sort of compiled inside the CPU. x86 is a funny architecture. So they kind of compile their instructions as they come in. They compile them into lower level instructions, and then they run those. So it's not an atomic operation, even though it looks like a single line. But then there's this lock prefix. Let's see if we can. It's probably hiding in here somewhere. There, lock. So if you say lock and then incl blah, then it's an atomic operation. Okay, so on Intel we apparently have support for doing this right away. Right. You can do atomic increments, but they're still really expensive because your pipelines are going to stall and you have to coordinate with all these other CPUs. It's a problem. Let's take a look at one more. I had one in mind. ARM64, yeah. So for ARM, so I think ARM64 is probably used in some of our recent smartphones. Probably even the iPhone 5S is a 64-bit ARM derived core, I think. So here, atomic increment, oh, that's just an atomic add. Okay, we add 1. So you see, what does that do? This is kind of curious. This doesn't look all that atomic. Right? Now we have 4 operations. Load, add, store, and then, I don't know what this is for. Like, it's checking if some value is 1. I have no idea what that does. Compare byte, not 0, or whatever. Okay, well, let's worry about this. Oh, yeah, it jumps back to here. So if it's not 0, it goes back to there. Okay. So on ARM, there's actually a completely different setup. This X here is exclusive. We're doing an exclusive read. Means once you start fetching this value out of, or is it that value? Probably that value. Out of memory, then no one else is allowed to use that memory address anymore. So no other program, probably no other core if you have multiple cores. It's just it. That's mine. Until you store, you do your exclusive store, and that releases the lock on this address. So we don't actually have to keep this. You don't have to annotate that in memory. That Lucas's idea is not bad, but it seems a little wasteful to put it in memory. It'd be nice to have it in the CPU. You just have a list of addresses that are already occupied and no one else can use at the moment. You check that first before you try to read from it. Okay, so that's the another way of doing an atomic add. It's atomic in the sense that it's locked, so it'll appear atomic to everyone. Right? It's not like single thing like a write of an integer. Okay, so anyway, that's our atomic inc. And of course we have another function that's the same. Decrement. And then we have, look at this. We've already used our compare and exchange. Compare, what do we call it? Compare exchange. Like this. So there you have some variable, the old value, the new value. And it returns previous value of bar. Okay, so you can you can imagine how this implementation of this function works. Right? It's actually not really a function, but it's a direct translation to assembly. You just give it these values, and assembly is the same opcode. Okay, and then we have two more functions here that we need to worry about today. We have our futex weight, and that takes, so this is called a futex, but it's really an address. Right? It's just an address. We give it an address, and the kernel deals with that as if it was a lock. Or not quite a lock, it's a futex. It's not really a lock. And then a value. So waits until woken up. If, let's see, futex value equals val. Okay, so this is sort of a little addition here. We're saying, okay, we can wait, but this is handy because things might have changed before we make this call. Someone else might have come in and released or signaled already for this. So it's a handy way of, sort of like with our condition variables, keeping some other integer that really stores the state of what's going on. So here we're saying we only lock if the value is still what we thought it was. If the value of this futex, I'll remove the adder. So we can go maybe like this even. Now it's so slow again. It's crazy. Okay. And then we have a futex wake up. Or just wake. And here we are able to give a number of threads that we want to wake up. So that, I suppose, is another handy function that we can use. These two are actually in the kernel. They don't look like this. It's a single system call with lots of parameters. But basically, one of the parameters is voice is awake or awake. And then so on. So we can ignore those details. So if we want to make a simple synchronization operation here, maybe we want to have something that allows us to just wait for a signal. So we'll start with a very basic operation. And let's see. Here we go. And make some drawings. I'm actually kind of cheating here. I'm copy pasting a little bit. Oh, that's what happens when you copy paste. It's too large. All right. So this function here it's almost like your condition variable to compile, because there's no locking going on. So this event class allows us to wait for something to happen and to tell that something has happened, and if so, you wake up those waiting. So it's a very basic method. So let's see what's going on here. When you're waiting, look at the value, our current value here. You say, if the value is the same, if our futex has the same value that we thought it had, that we think it has right now, then we'll just wait. So the reason that we're doing this stuff here is that something could have changed in between the call and when we were looking at it. Right? So it's not quite atomic, but at least we don't have lose the signal. Okay, so what's the signal doing? So now we have we're incrementing the value for some reason about that. We call duplex wait, and we try to wake up everyone. Everyone that's waiting. So if we call wait first, this all starts out with value equals 0. We call wait once. Now we're waiting for value equals 0. Everything's fine. We're just waiting. And then someone comes in, increments the value. That doesn't have any effect. And then calls wait, and then waits us up. But the neat thing about this value here is that, say I call wait, I call duplex wait, but it's not quite finished yet. Right? This is not atomic. So I'm in the system call, but now I have to yield the CPU to someone else. Now a signal comes in, it increments val, calls wait. Right? I'm still not in the list. So now I'm not going to get woken up. Later on, I get entered into this list and so on. Big problem, except the value was incremented. So before the kernel decides to put me in the list, it'll check that, oh, is the value what we thought it was? Right? Did the value remain the same? In that case, in this case, it isn't the same. So I don't get put in the queue. All right, so this would not have worked if it wasn't for the bounds. Right? If you don't have this value incremented, then we will wait forever in some circumstances. Very basic synchronization. Let's look at the lock then. So locks are, as we know, a lot trickier. Any questions on this, by the way?
I'm not sure what duplex wait is max.
Yeah, it tries to wake up everyone. So this account, right, if we go back to the previous good. Here, our Futex wake. It's a count that says wake up all the threads if you say int max. Actually, it doesn't quite say wake up all the threads, right? It says wake up to 4 billion or so threads. It's probably about the same on most machines. Okay. Any other questions on this thing here? Maybe a question, yeah. Oh, what is this doing? That. Oh, that's a constructor. Yeah. So for some reason, this guy decided to do it in C++. But right. So are we fine with that? Yeah. So the constructor does this little weird assignment way that they do in C++. This is the initial value of the member variable val, which is down here. So, yeah. Right. Okay, so the reason that we're doing all this, because I'm seeing a few people kind of fading out here. The reason we're doing all this is, how does this all, like, we're trying to implement synchronization operations in pthreads or in user space, but we don't have scheduler access, right? We don't get to control the scheduler. On the other hand, we don't want to have our kernel to have to implement every possible synchronization operation that we can think of. You could imagine doing that. You do a system call every time you want to do a barrier or a condition variable or a semaphore or this and that, right? System calls are expensive. And then you don't really know, when you're writing a kernel, you don't really know what synchronization operations your user space is going to want, right? Every program might have their own requirements. And it's nice to have this isolation as well. You can improve pthreads without having to break the kernel. Okay, so here we're giving a sort of a minimal system call interface that allows for all sorts of different synchronization operations. So this is a very basic synchronization operation. It wouldn't work if we didn't have these values to guard against the race condition here with the wait. We might end up waiting forever. Actually, let's do something even simpler. If we don't have the value here, we just leave it at 0. We don't increment it. If you get a signal first, and then you wait, you're going to wait forever. Right? So you really have to know sort of the order here. What is it that we're waiting for? And that's what this value is for in this case. So let's try to do something similar for a mutex then. Those are a little more familiar. So this is pretty hairy stuff, so we'll take it slow. We may not make it all the way through today. Looks pretty simple. Okay, so let's start with the unlock. So the value here is just saying, looks like it's the value keeps going up. Right? But whenever we unlock, we set it to 0. So 0 means it's unlocked. Right? A non-zero value means it's locked, but they could be locked a different way. Okay, so we set it to 0, and then we wake up one thread. That seems reasonable. Right? We don't want to wake up everyone, because only one gets to use it anyway. It could be a waste of time. We wake Maximus, and everyone's going to wake up and realize that they're just going to get this one. So you wake up one. Unlock is pretty straightforward. Unlock the lock. So remember, this atomic ink returns 0. And this is not a system call, the atomic ink. It's just that little bit of assembly. It says lock, and then what's it? Ink. So, but it's going to return whatever value used to be back. So if it was 0, we'd get a 0 back, and we break out of its loop. But we'd also have incremented the value. So now we went from 0 to 1, and then we break out of the loop. Pretty nice. Now it's locked. So it's really fast, right? So now we hold it. Later on we unlock, set it back to 0, wake someone up. And they're going to get it right away too. If they're the only one running at the moment, they're going to get it right away. They just do this atomic increment. There's no contention for it. Happens right away. It was 0, they get it done. Really. If it's not 0, if it didn't used to be 0, right, then that means someone else is already holding the lock. So we gotta wait. And we'll wait with a larger number. What's that?
Someone unlocks it.
Reaches 0 when it gets unlocked. Why do we wait for a value larger than C?
Is it because the value of val that we currently think it is C plus 1?
Yeah, exactly. So what came back from atomic ink here was the previous value. But we did an atomic ink, so that's going to be, of course, one more. All right. See any problems with this?
What did wait do? It compares the C plus 1 with val, and then if they're the same, they wait.
Yeah, so if when it's about to stick you in that queue, if the value at that moment of val is the same as C plus 1, then it'll wait. Otherwise, it'll just return. And then you have to check again, right? So there are some significant problems with this implementation.
Would that ever be similar with
when someone came in and unlocked.
Does it do the
It does, but atomic ink returns the value before they
leave us the machine down a bit while it's checking for the equal zero condition? You're running an atomic ink instruction inside of a while loop. It's going to really slow things down.
But we're doing this wait. Right?
Okay.
So that actually sticks as soon as it's not 0, we go in here. If it is 0, then we're out. We're done. If it's not 0, we go in here, assuming that this Qtex wait actually waits, which it will most of the time. Then we're not using any CPU there. That's okay. There's one really serious bug in here. There's one thing that makes things quite slow. And then I think there's one more bug. Let's see here.
Well, you guarantee that the atomic increments atomically, the compare is not locked around. So two things might go into the while loop just before Qtex wait actually gets run.
So you could imagine, yes, that you have two of them running this back to back, and then they both running Qtex wait. But the increment was still atomic, so that's correctly incremented to some value, and they will have two different Cs. So one of them isn't going to wait. Right? It will be the wrong value, so they'll return and try to do it again. So that's okay. Let's start with the kind of easier, simpler one first. What happens if you run this loop many times?
Get a really high value for C.
Yeah.
It might move around.
Or you could have this many threads, and still you get high value for C. At some point, if you get a little unlucky, you could end up with a C that's larger than 4 billion, whatever it is, 2 to the power of 32.
So it moves around, it becomes 0.
And then suddenly it's unlocked. Great. Alright, so you know, this it seems like, okay, big deal. Right? How often is it going to happen? But then, if that one time you happen to be doing some important thing, you rely on these things actually working. So it has to work every time. This one does not work when the count goes slow to 1.
Because it cycles from 4 billion to 0, is that?
Yeah, that's what happens when you increment from 2 to the power of 32 minus 1, right, plus 1, then you're at 0 again. So we actually can't have this sort of increment going on here. In order for this to work, we need to bound the value.
Could you what does C do? It goes to 4 billion and then loops to 0?
That's how.
Sure.
That's what integers do. Oh, sorry, maybe loops to negative values first. Yeah,
Yes.
good.
I
And then
think
eventually we get to 0.
I think it's a compiler thing where it actually goes to 0.
How did the compiler get involved in this?
Okay, maybe not compiler, but like I was actually listening on 251 lab or something, and they were using this to like implement the hash table because
And they probably had it unsigned.
Yeah.
If it's unsigned, then
Oh yeah, maybe those ones. Yeah.
either way, it doesn't matter, signed or unsigned. Eventually, you keep incrementing a negative value, it will go to 0, and then you have the same problem. Okay, so that's one problem that needs fixing. There's another problem. This is called a light block. Anyone spot the light block? We talked about light block before, I think. And in a light block, people are doing stuff all the time. They're just working really hard, but they're not making any progress. Pretty close to what you just spotted.
Could it be that when it does get to 0, they all try to leave it at the same time and it's not 0? And they wait, and then when it does become 0, they.
So, see, if they're waiting, only one of them is going to get woken up. So then we're in pretty good shape.
You were saying that if the number didn't match, they would basically fail and go back to life, right? What if this happens a lot?
Yeah, exactly. So now, enter here. First thread enters here. Increments goes down here. Doesn't run this quite yet. Next thread enters here. Increments goes down here. Now the first thread runs it. Sees that, okay, it wasn't the same value. Okay, I'll just return it. So now we're back in the while loop. We increment it. Go down here. Next thread, that is the second thread, runs this. Sees it's not the same value. Returns back up. So now you have two threads spinning like crazy. And it's not actually that unlikely to just continue forever. If you have more than two threads, all they're doing is going in there and returning at the same rate every time. They go in, they check, they return. Go in, check, return. So if they're kind of in lockstep, it's not going to happen all the time, but if they're in lockstep when they start, they're going to probably stay in lockstep. So you could end up with a light lock, and you're going to work really hard, and you'll never get out of your lock function. And then there's one more problem. It's not a bug. It's more of a performance problem. Look at this. Unlocking and recalling futex wait, even if there isn't anyone there. So this is a system call here. Those are expensive things. We don't want to be calling a system call if there's no point. So we actually need to track how many, is there anyone there waiting? Not how many, maybe. But if there's anyone waiting, then we wake them up. If there's no one waiting, okay, don't wake them up. Right? Okay, so now if we want a correct, okay, sorry. The correct implementation will have to wait. We're out of time. So next time we'll talk about the correct implementation, and maybe, if it's interesting enough, we'll also look at the correct but even more efficient implementation. Yeah.
Basically, what's a ballpark number for how many threads could possibly be waiting on something?
Thousands. You have a web server, and you decide to do a forking parallelism. Every incoming request.
Any kind of maximum that the processor would say there is?
Oh, processors don't care about threads.
Right, scheduler for OS.
Yeah, so you can have a thread limit in your OS, but you don't have to have it. So you can have thousands and thousands. All right, see you Wednesday.